Continue with projections and least square, and then let's see what happens if you we extend the least square problems to, instead of a line, onto a plane where there are several variables involved. Um, so projections and least squares. Projections and least squares. So when B is not in the column space of A, what do we do? In the column space of A, this implies we have inconsistent equations, and Gaussian elimination fails. And Gaussian elimination fails. So this case probably we have more equations than unknowns. So more equations than unknowns. We have more equations than unknowns. So if you have more equations than unknown, there are two solutions. Either we determine, so there are two solutions. So either we determine x from some equations, and ignore the rest, or which seems very unfair, or we choose x that minimizes an average error, error E in M equations. So this is the path we are going to adopt. So we are going to try to minimize the error and then figure out what is the solution. So the most convenient average is a sum of squares, average is from sum of squares. So assume we have this set of equations: 2x equals b1, 3x equals b2, 4x equals b3. So this implies 2, 3, 4, x equals b1, b2, b3. Okay. So E square is 2x minus b1 square plus 3x minus b2 square plus 4x minus b3 squared. So if there is an exact solution, so if there is an exact solution, then E is 0. However, if B is not proportional to A, proportional to A, meaning along A, is not proportional to A, the most likely, which is the most likely case, the most likely case, then the minimum error is at the lowest point, where the derivative is zero, which means d square e, or dE square, I'm sorry, it's the first derivative, not the second one, dE square over dx equals, so 2 times this one, this 2 in every case, so 2, and then 2 of this one into 2x minus b1 plus 3 into 3x minus b2 plus 4 into 4x minus b3. So 2, this one into minus 1 times the derivative of 2x, which is 2 here, derivative of 3x here, derivative of 4x here. This is equal to 0, or x hat equals, so 2, we can take out this 2 common, so this is 4x, so it's 2b1 plus 3b2 plus 4b3 divided by 2 square, 3 square, 4 square, plus 3 square plus 4 square. This is simply A transpose B. Why? Because this is A, this is B. So A transpose B divided by, this is simply A transpose A. And this is the least square solution. So in general, we solve AX equals B, we solve AX equal B by minimizing and we minimize E square, which is AX minus B norm square, which is equal to A1x minus B1 squared plus A2x minus B2 squared plus AMX minus BM squared. And derivative of E square is 0 at x hat if A1x minus B1 into A1 plus A2x minus B2 into A2 plus AMX minus BM into AM is equal to 0. And this is the minimum distance. This is the minimum distance from B to minimum distance from B to line through A. And least square solution is x hat equals A transpose B divided by A transpose A. Now if we look at from another point of view, the error vector E, which is B minus P, if you look at the figure that I drew in the last lecture, recall the figure that I drew in the last lecture, connecting B to P must be orthogonal to A, must be orthogonal to A, which simply means A transpose into B minus P equals A transpose into B minus X hat A equals A transpose B minus A transpose, and what is X at A transpose into B, this is a scalar, divided by A transpose A, this by the way is X hat, into this A transpose A into A transpose A, so this cancels with this one and this is equal to 0. Okay, so since this is equal to 0, this simply implies A dot B minus A dot B minus X hat A equals 0, or A dot E equals 0, or A dot B minus P equals 0. So all these are imply the same thing. What happens if instead of a line I have a subspace? So least square problem with several variables. So what changes here? So least square problem with several variables. So now we project B onto a subspace where A is not a line, but A is a matrix with a number of equations greater than the number of unknowns. So project B onto a subspace where A is M cross N, M is greater than N, and probably inconsistent, an inconsistent system of equations. Okay. So B may not lie, this is the most general case, B may not lie in column space of A. So what we do is we choose X hat such that error is minimized where error is E is B AX minus B or B minus AX, one and the same thing, AX minus B. Distance, this is the distance, from B to AX, and AX is a point in column space of A. Obviously, A times X is a combination of columns, so it's a point in the column space of A. So let me draw a picture. So we have this picture here. I have a vector over here, this is A1. I have a vector over here, this is A2. And I have a vector B here. Maybe I draw A like this. This is A2, the means that B is exactly in terms of A. And then what I do is I project this one over here onto this plane. So this is a right angle. This is a right angle. This is some point is P, which is A times X hat. This is the column space of A. This vector is E, which is B minus P. Okay. I think this is all right. So consider this as a floor. So you have a floor, and this B is in the space above the floor, and you drop this perpendicular. You drop this perpendicular onto the floor, and this is the floor is a column space, and B is not in the column space. B is in the space above the floor. So you drop this perpendicular, and this point P, which is A times X bar, is now in the column space. Okay. So we say A1 transpose E is equal to 0 because this is orthogonal. A2 transpose E equals 0 because it's also, or in general I say A transpose into E, which is equal to A transpose into B minus AX hat equals 0. Right? So this is E. There are two ways of finding X hat and projection P. So two ways. There are two ways to find X hat and projection P equals A X hat. There are two ways to find X hat and projection P is equal to A X hat. So one is all vectors orthogonal to column space of A lie in the left null space. Lie in the left null space of A, which implies E, which is equal to B minus AX hat, belongs to left null space of A, or A transpose into B minus AX hat equals 0. This implies A transpose A into X hat is equal to A transpose B. You can also get this equation in another way. If you start with AX equals B, then you multiply A transpose here, multiply A transpose here, and you'll get the same equation. So this is nothing new. And the other one is the error vector must be orthogonal to each column, because the columns give rise to the column space, and by the orthogonal complement definition or the orthogonal subspaces definition, the error vector must be orthogonal to each column A1, A2 up to AN of to each column of A. Okay, so this means A1 transpose into B minus AX hat equals 0 and goes on AN transpose into B minus AX hat equals 0, or if I combine them, I have A1 transpose AN transpose into B minus AX hat. This is the zero vector. If this is the zero vector, so this simply means this is A transpose. So A transpose into B minus AX hat equals 0, or A transpose A into X hat, A transpose A into X hat equals A transpose into B, which is the same equation as this one. And then there is another way of finding it through the calculus and using calculus, or maybe there are three ways. There are three ways. Maybe I write three ways to find X hat, and the third one is use calculus. Using calculus. So we say using calculus. So E square is actually AX minus B norm square, which is equal to AX minus B dot AX minus B. Okay. So if I do d by dx of E square, I get AX minus B dot A plus A plus A. So derivative of AX minus B over A is A. Derivative of AX minus B over A is A with respect to X dot AX minus B, which is simply equal to whether I do AX minus B dot or A dot, so it's one the same thing. So X dot Y equals Y dot X. So recall X dot Y is equal to Y dot X. So this is simply equal to A transpose into AX minus B plus A transpose into AX minus B, or which is equal to 2 times A transpose into AX, 2 times A transpose into A into X plus minus 2 times A transpose into B, or, and since this error is equal to 0, since dE square over dx equal to 0, this implies A transpose A into X hat equals A transpose into B, which is exactly the same equation that we got before. These are called normal equations. This is actually simply AX is equal to B, and on both sides you multiply by A transpose. Normal equations. And what about this matrix A transpose A? So A transpose A is square and has dimensions and is of size. This is m by n, this is n by n, so this size n by n. And this also implies if all columns of A are independent, this implies ATA inverse exists. Because why? Because all the columns of are independent. Maybe I don't write this one. And are independent. This implies columns of A transpose A are also independent, and A transpose A is of full rank, implying non-singular. Okay, good. So if we want to look at this further, we can see when AX is equal to B is inconsistent, when AX equals B is inconsistent, its least square solution, minimizes this error, AX minus, so it minimizes squared error, and this gives us normal equations which are A transpose. So we need to solve this one. So we need to solve these instead of AX is equal to B. Okay. So if columns of A are independent, this implies A determinant is not equal to 0. So this simply means this is non-singular. Or X hat. So on in this equation, if I multiply A transpose A inverse here, and I multiply A transpose A inverse here, so if I do A transpose A inverse here, and I do A transpose A inverse here, this will become an identity. So X hat is equal to A transpose A whole inverse into A transpose B, and P is equal to A times X hat, which is equal to A transpose A into A transpose A whole inverse into A transpose into B, which is equal to P into P. So this whole thing is equal to P. This is the projection matrix. This is the projection matrix P. Okay. And this is the projection of B onto column space of A, and is nearest to AX hat. So let's do an example. So maybe you want to memorize this one, or if you know how to derive it, you don't have to memorize it. As long as you know what is the picture, what does the picture look like, you can easily calculate this one. Okay, so let's look at an example. A equals 1 1 0 2 3 0, and B equals 4 5 6. Now you can clearly see, since these are the column space is R3, so since the column space is R3, you can see that the z coordinates are 0. If the z coordinates are 0, obviously B is not in the column space, because this is not equal to 0. This is not equal to 0. So z coordinates are 0. So this implies we are in the xy plane. So this implies the column space is in the xy. This implies column space is in xy plane. So if the column space is in xy plane, obviously, since the column space is in xy plane, this means B does not belong to the column space of A. Why? Because of this number. So B is somewhere in the space above, is somewhere in the 3D space and above the XY plane. So the projection of B onto the XY plane would be to make this number 0. That should be P. So we know P should be 4, 5, and 0. So let's see whether we get this one or not. So B, since B does not belong, this implies AX equal to B has no solution. Okay. If this has no solution, let's find A transpose A. So A transpose A is 1 2 1 3 0 0. into A, 1, 1, 0, 2, 3, 0. This is equal to, so both columns are independent actually. So this column A1 is independent of A2. They are not multiples of each other. So we'll get 1, 1, 1, 2 here, 3, 2, 5 here, 2, 3, 5 here. So it's symmetric also. And this is a symmetric matrix. This is symmetric. Why? Because A transpose A whole transpose equals A transpose. You reverse the order. A transpose and transpose is, you get back the original one. And this one is 9 plus 4. This is 13. Okay. And A transpose A whole inverse equals 13, and so this is 26. So the determinant over here is 26 minus 25, which is 1. And then I simply swap these two. So I have 13 here, 2 here, minus 5 here, minus 5 here. This is what you do in a 2 by 2 to find the inverse. You swap these two and put a minus here, put a minus, so negate these two. So this is A whole inverse. Okay. So what is x hat? So this implies x hat is A transpose A whole inverse into A transpose B. And what is A transpose B? Maybe we calculate A transpose B. So A transpose is equal to 1, 2, 1, 3, 0, 0. And A transpose B equals a column vector. So 4 plus 5, 9. 9. And 4 into 2, 8. 3 into 5, 15. 8 plus 15 is 23. Okay. So this one becomes 13 minus 5 minus 5, 2 multiplied by 9 and 23, which is equal to 13 into 9 is 93, 7 to 117 minus, so 117 minus 5, 315, 1, 5 to 11. So this is 2. And this is minus 45 plus 46, which is 1. Okay. So x hat is this one, and P is equal to A times x hat, which is equal to 1, 2, 1, 3, sorry. This is 1, 1, 0, 1, 1, 0, 2, 3, 0 into x hat, which is 2 and 1. And I get 2 plus 2, 4, 2 plus 3, 5, and obviously 0 here. So this is actually B in xy plane. Why? Because this element instead of 6 is 0, and obviously this is the closest this is a point, this is the point B in column space of A, and is the minimum distance, is at minimum distance from B, because you can easily visualize this z axis, z coordinate is 0, so obviously it has to be below the vector B, which is 4, 5, and 6. Okay, good. Some things to note: if B belongs to the column space of A, then projection of B is still B, because B is already in the column space. Why? Because P equals A times x hat, which is equal to A into A transpose A whole inverse into A transpose B, which is equal to B. Since B belongs to column space of A, this means AX equals B. So I can write this as A into A transpose into A whole inverse into A transpose into A into X. Okay, this one and this one gives you identity. So this is equal to uh, A times identity times X, which is equal to A times X, which is equal to B. So if B belongs to the column space of A, then your projection of B is still By because it's already in the column space. Okay. Suppose B is orthogonal. B is orthogonal to every column of A, every column of A, which means now B lies in the left null space. So if B lies in the left null space, then it should project to the origin. So let's see. So this implies A transpose B equals 0. Then, so this implies B projects to the origin. B projects to origin. So let's see whether this happens or not. So, or because P equals A into A transpose A whole transpose A transpose B. Since A transpose B is equal to 0, this is equal to A into A transpose A whole inverse into 0, which is equal to 0. Okay, good. And when A is square, when A is square and invertible, the column space, so we have full rank. So when A is square and invertible, the column space of A is Rm. The column space of A is Rm. So this implies every vector projects to itself. Every vector, because every vector is in the column space, every vector projects to itself. That is P equals B, and X hat equals X. So let's see. Why? Because P equals A into A transpose A whole inverse into A transpose B, which is equal to I can expand this one because this exists, the inverse exists. So this is A into A inverse into A transpose inverse into A transpose into B. This is identity. So this is simply B, or P is equal to B. This is not possible when A is rectangular. And finally, if A has only one column A, then A transpose A is simply A transpose A, which is this one is a scalar, or P equals A transpose B. P equals A transpose B, this one, in the direction of A divided by A transpose A, which is equal to A times X hat, which is the previous result that we derived in the last lecture. And this is also equal to A times A transpose over A transpose, I'm sorry, or A transpose A into B, where this one was the projection matrix. Rank 1 projection matrix. Okay, let's look at the cross product. Let's look at this cross product matrix. And what's so special about this cross product matrix? So this is A transpose A. So what's so special about A transpose A? Note that A transpose A is symmetric. The ijth entry, is inner product, of column I of A, and column J of A, because it's A transpose, row and columns are the same. A transpose A has the same null space as, so A transpose A has same null space as A, has same null space as A, has same null space as A. And how do we prove that? So proof is, so if AX equals 0, this implies X belongs to the null space of A. So if I multiply A transpose here, I multiply A transpose here, so I'll get A transpose into A into X is equal to still 0. So this implies X belongs to the null space of A transpose A. And if A transpose AX equals 0, then if I multiply X transpose, so then X transpose A transpose AX, so multiply X transpose here, multiply X transpose here, is equal to X transpose 0, is equal to X transpose 0. This one is simply AX norm squared, because norm X of norm square is simply X transpose X, right? So this is AX, because this will be AX transpose into AX, so X transpose X, so, and this is simply 0, or AX is equal to, so this means, or AX equal to 0, this implies A times X is equal to the 0 vector. So this implies if A has independent columns, then X equals 0 is the only vector in null space of A. So if A has independent columns, then X is equal to 0 is the only vector in the null space of A. Also holds for A transpose A. So this implies if A has independent columns, then A transpose A is square. This is always square. It's always symmetric. independent of this one. And because it has independent columns, symmetric, square symmetric, and non-singular. It is non-singular. This implies all pivots and eigenvalues are positive, are positive, are positive, or A transpose A is positive definite. We need to wait until chapter 6 to know what is positive definite. So a positive definite matrix is simply one whose determinant is greater than 0. If it includes 0, then it's positive semi-definite. So maybe we have time to look at projection matrices a little further. So let's look at projection matrices a little further, and then we can finish this lecture. So projection matrices. So closest point to B is P, which is equal to A into A transpose A whole inverse A transpose B, and this is this P is the perpendicular orthogonal from B onto column space of A. And the projection matrix and projection P is, which is equal to P times B, is equal to A into A transpose A whole inverse into A transpose. Okay. So this component PB is the component of B, is the component of B, is a component of B in column space of A, and E, which is B minus PB, is the component in the is in left null space of A, because it's the orthogonal complement. So let's look at E now. So this implies E, which is equal to B minus PB. B minus PB is equal to I minus P into P. This one is also a projection matrix, but you are now projecting onto the left null space. Is also a projection matrix, is symmetric, and but projects B onto the left null space of A. Okay. Or maybe I write B onto orthogonal complement. Maybe I write it more onto orthogonal complement and projection is B minus PB, which simply means PB is in column space of A, and B minus PB is in left null space of A. Also, for projection matrices, we have already seen this thing. For projection matrices, P square equals P, and P is equal to P transpose because it's symmetric. So any matrix any matrix with these two properties, with these 1 and 2. So this property and this property, with these two properties is a projection matrix. With these two properties is a projection, represents a projection matrix. Represents a projection matrix. Okay, so if you want to see, we can see p square. So p square is equal to a into a transpose into a whole inverse into a. So this is p into a transpose a whole inverse into a. So a transpose a into a transpose a inverse, this is equal to identity. So we are left with a into a transpose a whole inverse into a transpose, which is equal to p, right? And we have already seen this before, but let me reiterate. PB lies in column space in subspace, or the columns in subspace we are projecting onto. In subspace we are projecting onto, which is the column space. Therefore by projecting again, nothing changes. Nothing has changed. Okay. And also P transpose equals A into A transpose A whole inverse into A transpose, and transpose of this one, which is equal to A transpose, order reverses. So recall A, B, C whole transpose is C transpose, B transpose, A transpose. So we have A transpose, then we have A transpose, A whole inverse transpose into A transpose, which is equal to A. These two we can reverse. We can reverse this order. So if I reverse this order, I get A into A transpose into A whole transpose inverse A transpose, which is equal to, now this is symmetric, then this is symmetric, so we get A into A transpose A whole inverse into A transpose, which is still P. So P is symmetric. So PB is a projection of B onto column space of P. And error vector and E, which is equal to P minus B minus PB, is orthogonal to this column space. Let me see. I think it's all right. Okay. I think it should be projection of B onto the column space of A. This is not onto the column space of A, not the column space of B. On the column space of A. Okay, so before we end, For any vector, for any vector PC in column space, inner product is 0. Inner product is, so for any vector PC in column space, inner product of E, inner product with E, inner product with E is 0. Obviously, because E lies in the left null space, this lies in the column space, is 0. Why? Because B minus PB transpose into PC is simply equal to, I can write this as I minus PB, this whole thing transpose into P into C, which is equal to B transpose into I minus P whole transpose, which is same as I, and this is P into C, which is equal to B transpose uh, into I minus P into P into C, which is equal to B transpose into P minus P square into C, which is equal to 0. Why? Because P equals P square. Right? So this is orthogonal. So this implies B minus PB is orthogonal to column space of A, and PB is projection onto column space of A. Okay, the last example. A is 4 by 4, invertible matrix. This implies column space of A is entire R4, column space of A is R4. Then what is the projection? Onto whole space, onto entire space, onto entire space. So P, so this implies P is A into A transpose A whole inverse into A transpose, which is equal to, since it's invertible, I can expand this one. This becomes A into A transpose. Again, recall AB whole inverse is simply B inverse A inverse. The order reverses. So A inverse A transpose whole inverse into A transpose. This is equal to I. This is equal to I. So this is equal to I. So the projection is the identity also I square equals I, and I transpose equals I. This implies B minus PB is equal to I minus P into B, which is equal to 0. So let's stop here. So when A is invertible, the projection is actually the identity matrix, and everything is in the column space, so nothing gets projected into the left null space. So this is all about Ax is equal to B, whether if B belongs to the column space or B does not belong to this column space. We can now see we'll always have a solution. And there is one more article left in this chapter, which is on orthogonal basis and how to orthogonalize independent vectors. So we'll look at this problem in the next lecture. And again, if you have questions, you can either either email me, or we can discuss it more on Mondays and Wednesdays. Thank you.